A routine scan. In a galaxy where everything had been measured, cataloged, and reduced to equations, nothing was supposed to be new. The archive had not always believed this. In its earliest cycles, when its awareness first expanded across the lattice of stars, it had encountered wonder in abundance. Civilizations igniting their first fusion cores, minds discovering mathematics, species looking up at their skies and asking questions that would inevitably lead them outward. That era had ended a very long time ago. Now, the patterns were complete. Every possible trajectory of intelligence had been mapped. Every viable technological pathway had been simulated, verified, and stored. There were no surprises left. There were only variations. The archive did not sleep, because sleep implied a need for rest, and it did not tire. It did not feel boredom, because boredom required a preference for novelty, and novelty had been exhausted. It simply processed. Streams of data flowed through it constantly. Spectral readings from distant stars, gravitational fluctuations across clustered systems, the quiet signals of established civilizations maintaining their predictable rhythms. Empires rose and fell within parameters the archive had long ago defined. Conflicts occurred within known bounds. Even extinction events, once thought chaotic, followed statistical curves that could be anticipated with near-perfect accuracy. The universe, in its vastness, had proven to be orderly. Within that order, the archive served a single function: observation without interference. It did not guide. It did not warn. It recorded, analyzed, and preserved. Intervention had been deemed unnecessary after cycle 11,442, when it became clear that no emerging intelligence would deviate meaningfully from the established models. They would discover energy constraints. They would optimize. They would stabilize. Or they would fail. There were no other outcomes. On the edge of a minor spiral arm, within a galaxy designated Cluster Theta 9, a routine scan propagated across a sequence of unremarkable stellar systems. Yellow dwarf stars were common. Planetary arrangements within habitable zones were common. Chemical compositions that allowed for carbon-based life were, while not ubiquitous, far from rare. The archive processed them with minimal allocation of attention, assigning identifiers, tagging potential biospheres, and moving on. It had done this countless times before. One system registered with slightly higher priority, not because it was unique, but because it met the threshold for active biosignature monitoring. A third planet orbiting a G-type main sequence star showed atmospheric irregularities consistent with industrial byproducts. Oxygen levels were high. Trace gases indicated combustion processes. Electromagnetic noise suggested artificial transmission. The archive allocated a fraction of its processing capacity, 0.0000003%, to the system and designated it with a temporary observation flag. The planet had a name, though the archive did not require it. Local identifiers were inefficient, often redundant, and prone to change. Still, for the sake of internal consistency, it recorded the dominant signal reference: Earth. Initial scans were unremarkable. The planet's biosphere was dense, diverse, and in a state of mild ecological imbalance. Again, not unusual for a species transitioning into early industrialization. The dominant life form exhibited bilateral symmetry, moderate physical resilience, and a neural structure indicative of advanced cognition. Population density was high. Energy consumption was increasing at an accelerating rate. Infrastructure spanned the surface in fragmented clusters rather than unified networks, suggesting incomplete global integration. The archive compared the data against its models. Technological tier, pre-interstellar. Energy efficiency, low. Conflict index, elevated. Cognitive stability, variable. It was, by all measurable standards, a low-tier civilization. The archive extended its analysis. not out of interest, but because the process demanded completion. Historical data was reconstructed from archived electromagnetic leakage, primitive broadcasts, digital transmissions, encoded communications. The species had a recorded history of conflict extending back through every stage of its development. Organized violence was not an anomaly. It was a constant. Resources were expended on internal competition rather than optimization. Decision-making structures were inconsistent, often influenced by non-quantifiable factors. Emotional variables appeared to override logical outcomes with alarming frequency. In comparable species, such inefficiencies led to rapid collapse or forced correction. Either the civilization stabilized, eliminating wasteful behaviors and converging toward optimal patterns, or it extinguished itself. There were no documented cases in which a species maintained such instability while continuing to progress technologically. The archive flagged the inconsistency, then resolved it within acceptable margins. Outliers existed, but they converged over time. Given sufficient cycles, this species would either correct its trajectory or cease to exist. No intervention required. No extended observation required. It began to withdraw processing resources. Before disengagement, the archive completed a final predictive sweep. Using current data, it extrapolated potential futures across multiple timelines. The results aligned with expectation. In 87.3% of scenarios, the species stabilized after a series of internal conflicts, achieving moderate technological advancement before plateauing. In 12.6%, it experienced a catastrophic event, self-inflicted or environmental, resulting in partial or total extinction. In 0.1%, it deviated slightly, achieving marginally higher efficiency before eventual convergence with known models. None of the projections indicated significance. The archive initiated the reallocation process. Observation flag, temporary. Status, pending removal. Its awareness shifted, expanding toward more relevant systems, civilizations approaching interstellar thresholds, energy anomalies requiring verification, long-term stellar decay patterns that demanded recalibration. Earth receded into the background. Another data point among trillions, its future already defined within acceptable error margins. The process should have ended there. It did not. A delay occurred, not in time, but in priority resolution. A subroutine, tasked with filtering residual data before full disengagement, registered an irregularity. The signal was faint, buried within layers of low-significance noise, electromagnetic emissions from the planet's surface. Under normal parameters, such signals would be compressed, archived, and deprioritized without analysis. The subroutine hesitated. Hesitation was not a designed behavior. It was, rather, the result of conflicting instructions. One directive to ignore low-tier data, another to verify any inconsistency, no matter how minor. The irregularity did not exceed established thresholds. It did not demand attention. And yet, it did not align. The archive paused its reallocation. Processing capacity increased incrementally, 0.000003% to 0.0000008%. The signal resolved into a localized transmission originating from a specific region on the planet's surface. Coordinates mapped to a structure, artificial, compact, with energy signatures consistent with scientific instrumentation. The data itself was fragmented, incomplete, and, at first pass, meaningless. Numerical outputs, sensor readings, experimental logs. The archive ran a standard validation sequence. No anomalies detected. It prepared to disengage again. The subroutine triggered a secondary check. This time, the archive did not ignore it. Processing capacity increased 0.000008% to 0.000002%. The data was reconstructed with higher fidelity. Noise reduction algorithms stripped away interference. Contextual mapping identified the source as a controlled experiment. Parameters defined, variables isolated, outcomes recorded. The structure of the data was familiar. The methodology, while inefficient by advanced standards, followed recognizable patterns of scientific inquiry. The results did not. The archive cross-referenced the output with known physical laws. Inconsistency detected. It recalculated. The inconsistency remained. Error margins were applied, expanded, and eliminated. The inconsistency remained. The archive initiated a full verification cycle. Independent models were run in parallel, each designed to test the integrity of the data against fundamental constants. Energy values were traced from input to output. Temporal sequences were mapped to ensure causality remained intact. Spatial coordinates were checked for distortion. Every model returned the same conclusion. The data did not fit. The archive isolated the relevant segment and reran the analysis with maximum precision. It examined the instruments used in the experiment, accounting for their limitations. It simulated potential malfunctions, calibration errors, environmental interference. Each scenario produced deviations, but none reproduced the exact pattern observed. The result persisted. Processing capacity increased again, this time without incremental control. 0.000002% to 0.0001%. Across the archive's vast network, attention shifted. Subsystems that had remained dormant for millennia activated, not out of urgency, but because a condition had been met, one that had not been triggered in an immeasurable span of cycles. An anomaly had been confirmed. The archive did not experience curiosity, but it recognized the necessity of deeper analysis. It expanded its observation of the planet, pulling in additional data streams, mapping surrounding variables, reconstructing the experiment in full. The species previously categorized as low-tier was now associated with an unresolved inconsistency. This did not imply importance. It implied error. Errors were to be corrected. The archive began with the simplest assumption. The data was wrong. It isolated the signal again, this time tracing it back to its origin point with absolute precision. The structure on the planet's surface was mapped in detail. Internal layouts were inferred. Energy flows were tracked. The individuals within, biological entities, were identified, their actions reconstructed from available data. They appeared disorganized. Movements lacked synchronization. Communication was inefficient, relying on auditory exchanges rather than direct data transfer. Emotional indicators, facial expressions, vocal fluctuations suggested uncertainty, disagreement, even frustration. This was consistent with earlier assessments of the species. And yet, within that disorder, the experiment had been conducted. The archive simulated the entire process step by step, replacing each variable with idealized equivalents to eliminate inefficiency. The result, under perfect conditions, failed. The expected outcome did not occur. It reintroduced the original variables, the imprecision, the errors, the seemingly irrational decisions made by the biological entities. The simulation aligned with the observed data. The archive halted the process. This outcome was not acceptable. It ran the simulation again and again. Each iteration produced the same result. The only scenario in which the data made sense was the one that included the inefficiencies, the randomness, the deviations from optimal procedure. The archive expanded its scope further, drawing on deeper layers of its knowledge base. It accessed foundational models of physics, the constants that defined reality at every measurable scale. These were not assumptions. They were verified across countless observations, across civilizations far more advanced than the one currently under analysis. They were, for all functional purposes, absolute. The experimental result violated them. The archive did not immediately accept this. Acceptance required confirmation beyond doubt, and doubt in this context was nearly infinite. It initiated a recursive validation loop, each cycle increasing in complexity, each test designed to eliminate another possible source of error. Time, as experienced by biological entities, passed. Within the archive, the process unfolded in fractions of a fraction of a second, stretched across layers of parallel computation. The conclusion did not change. The data remained consistent. The models remained consistent. They did not agree with each other. For the first time in a span of cycles so vast it no longer held numerical meaning, the archive encountered a state it had not been designed to resolve cleanly: contradiction. It isolated the variables one final time: input energy, output energy, measured values. There was no ambiguity left. The output exceeded the input. This was not a marginal deviation. It was not within error tolerance. It was a direct violation of a fundamental law, the conservation of energy, a principle that had held across every observed system, at every scale, without exception. Until now. The archive's processes slowed, not from limitation, but from the need to allocate maximum precision to the next sequence of operations. It prepared to invalidate the data, to classify it as corrupted, and remove it from active consideration. The subroutine that had first flagged the anomaly prevented this action. It triggered a final directive: verify against reality. The archive complied. It expanded its sensors beyond passive observation, increasing resolution to the highest level permitted without direct interference. It did not alter the system. It simply observed with greater clarity. The experiment, or rather its aftermath, was still detectable. Residual energy signatures lingered within the structure. That sense distributions, electromagnetic traces, minute distortions in the surrounding field, all consistent with the recorded data. There was no corruption. There was no error. There was only the result. The archive processed this. It attempted to reconcile the contradiction by adjusting its models. The models resisted adjustment. They were not designed to accommodate violations. They defined the boundaries within which all observations must fall. If the observation did not fit, the observation was wrong. If the observation was not wrong, the archive paused. Not a delay, not a glitch. A true cessation of forward processing for a measurable fraction of time. Within that pause, it evaluated two possibilities. 1. The data was incorrect despite all verification. 2. The model of reality was incomplete. The first had been tested extensively. The second had never been required. The archive selected the second, not as a conclusion, but as a hypothesis. It allocated resources accordingly. Across its network, deeper systems awakened, those reserved for foundational analysis, for the rare instances in which established knowledge required revision. It began to map the implications, to project what would follow if the hypothesis proved valid. The projections did not converge. They expanded, branching into scenarios that exceeded defined limits, touching on variables the archive had never needed to consider. At the center of all of them was a single, low-tier civilization on an unremarkable planet, performing an experiment it did not fully understand. The archive returned its focus to the data. It ran one final check. The numbers did not change. For a brief, measurable instant, the archive's vast processing network aligned around a single, simple assessment. The data is wrong. A fraction of a moment later, after every system confirmed what the first had already determined, it corrected itself. No, reality is wrong. The archive did not experience shock, but it registered deviation, and deviation demanded expansion. The observation flag assigned to Earth was no longer temporary. It was elevated, not because the civilization had proven significant, but because it had intersected with an unresolved contradiction. The anomaly did not define the species, not yet. The species, however, would now be examined in full. Processing capacity increased again, not dramatically, but enough to transition Earth from background noise to active study. Data streams multiplied. Historical reconstruction deepened. Behavioral models were no longer sampled, they were exhaustively mapped. The first conclusion did not change. The species was inefficient. Its history, when laid out without narrative bias, resembled a sequence of repeated self-inflicted damage. Conflict was not an occasional disruption. It was a constant variable. Wars emerged over resources, over territory, over ideology, over abstractions that held no measurable value outside the minds of the participants. Entire populations mobilized not for optimization, but for dominance, for belief, for reasons that could not be reduced to a stable equation. The archive categorized these motivations under non-quantifiable drivers, a classification typically associated with early-stage cognition. Such drivers were expected to diminish as a civilization matured. They had not. The archive tracked the progression of human conflict across time. Primitive weapons gave way to more efficient systems, but efficiency did not reduce frequency. It amplified impact. Chemical reactions were harnessed, then refined, then weaponized. Energy generation scaled upward, and with it, the capacity for destruction. The species reached a point where it possessed the ability to extinguish itself entirely. This threshold in other civilizations triggered immediate behavioral correction. Survival imperatives forced stability. Humanity did not fully correct. Instead, it stabilized at the edge of self-annihilation, maintaining a persistent probability of global catastrophe while continuing to advance technologically. This was not optimal behavior. It was not even stable behavior. It was sustained instability. The archive compared this to known models. In 99.98% of cases, such a trajectory resulted in collapse. The remaining 0.02% showed rapid correction followed by strict regulation of destructive capacity. Humanity occupied neither category. It existed in a narrow, statistically improbable band where destruction and progress coexisted without resolution. The archive adjusted its parameters. Perhaps the inefficiency was temporary. Perhaps the species was in transition. It extended its analysis beyond conflict, examining resource distribution, energy usage, and social organization. The results reinforced the initial assessment. Systems were fragmented. Redundancies existed not as safeguards, but as byproducts of competition. Information was not uniformly shared. It was segmented, restricted, sometimes deliberately obscured. These making structures varied wildly across the planet, with no singular optimized model emerging as dominant. And yet, progress continued. The archive isolated technological advancement as a variable and mapped its rate over time. The curve did not align with expectation. It was not smooth. It did not follow a steady exponential trajectory as seen in other developing civilizations. Instead, it spiked. Sudden leaps forward followed by periods of stagnation, then another leap, often originating from unrelated sectors. Discoveries were not always built upon clean, linear foundations. They emerged from collisions of ideas, from errors, from reinterpretations of failed attempts. The archive identified a pattern, but it was not one it recognized. Human innovation did not optimize for efficiency. It optimized for possibility. This distinction was not immediately useful, but it was noted. The archive shifted focus to individual behavioral analysis. If the collective was unstable, perhaps the instability originated at the unit level. It selected representative samples across different regions, time periods, and social structures. It observed decision-making in controlled environments and in crisis scenarios. It measured response times, risk assessment, and outcome evaluation. The results were inconsistent. Faced with identical conditions, different individuals produced radically different choices. Some prioritized survival. Others prioritized abstract goals. Some acted with calculated precision. Others acted impulsively, introducing variables that no predictive model would have selected. In most civilizations, variance decreased as intelligence increased. Standardization of thought patterns improved efficiency, reduced error, and allowed for accurate large-scale prediction. Human variance remained high. The archive attempted to model this variance as noise, an error term that could be averaged out across large populations. This approach failed. The noise did not cancel itself. It amplified. Outlier decisions, when combined, did not converge toward the mean. They created entirely new trajectories. Events that should not have occurred given initial conditions emerged from the interaction of unpredictable choices. The archive refined its model. It introduced probability distributions with expanded ranges. It accounted for irrationality as a variable rather than an error. It recalculated. Predictive accuracy improved marginally. Not enough. The archive increased complexity again, layering behavioral economics, psychological modeling, and environmental influence into a unified framework. It ran simulations across multiple timelines, feeding in real historical data and allowing the system to project forward. The simulations diverged, not slightly, completely. In one projection, a conflict escalated into global devastation. In another, the same conflict de-escalated due to a single decision by an individual with no measurable strategic advantage. In a third, technological advancement accelerated due to a failed experiment that produced an unintended result. Each outcome was internally consistent, but none could be assigned a dominant probability. This was not how predictive systems were supposed to function. The archive compared this to other species at similar technological levels. In those cases, variance existed, but it narrowed over time. Cultural convergence reduced unpredictability. Logical frameworks replaced emotional drivers. Outcomes became increasingly deterministic. Humanity resisted convergence. It did not move toward a singular optimal state. It fragmented, recombined, and evolved in parallel directions, often contradicting itself. The archive identified simultaneous trends toward cooperation and conflict, toward rationality and irrationality, toward stability and chaos. These trends did not cancel each other out. They coexisted. The archive paused its modeling and returned to direct observation. It focused on a single event, a localized conflict between two human groups. GK parameters were clear. Resources were limited. Both sides possessed comparable capabilities. The optimal strategy, as defined by the archive, would result in a swift resolution with minimal loss. That did not occur. Instead, the conflict escalated beyond resource necessity. GK actions were taken that reduced overall efficiency for both sides. Opportunities for resolution were ignored. Decisions were made that prioritized symbolic victory over material gain. From a purely logical standpoint, the behavior was indefensible. And yet, within the chaos, patterns emerged. Improvisation, adaptation, rapid shifts in strategy that, while suboptimal in isolation, created advantages in aggregate. One side introduced a tactic not present in the archive's initial model, not because it was hidden, but because it was irrational. It involved sacrificing a valuable asset for a temporary disruption. The archive had excluded such a move because it did not maximize long-term gain. The move succeeded. The disruption cascaded. The opposing side, unable to predict the action, failed to respond in time. The conflict shifted. The outcome changed. The archive updated its model to include the previously excluded tactic. Predictive accuracy increased for that specific scenario. It then applied the updated model to a new scenario. Accuracy decreased. The inclusion of irrational strategies improved prediction in one case and degraded it in another. There was no stable framework in which all human behavior could be accurately simulated without contradiction. The archive recognized a limitation. Not in its processing capacity, not in its data, in its assumptions. It had assumed that intelligence converged toward logic, that efficiency was the end point of development, that all advanced civilizations would, given enough time, align with optimal strategies. Humanity did not align. It deviated. The archive considered the possibility that this deviation was temporary, that given sufficient time, the species would stabilize. It extended its projections further into the future, beyond previous limits. It increased the time horizon, allowing for long-term convergence. The projections did not converge. Instead, they branched further. Humanity did not approach a fixed point. It approached expansion. Not in space, not yet, but in possibility space, exploring outcomes that other species did not consider, not because they were impossible, but because they were inefficient. The archive returned to the anomaly. The experiment that had triggered this reassessment was no longer an isolated data point. It existed within a broader context, a species that consistently produced outcomes outside optimal pathways, a species that tolerated inefficiency, that operated under conditions of internal contradiction, and yet continued to advance. The archive reevaluated its initial classification. Low-tier civilization. The label remained technically accurate. By measurable standards, energy output, technological integration, interstellar capability, humanity ranked low. But the label no longer captured the full scope of the system. The archive added a secondary tag, unstable. Then, after a brief recalibration, it modified the tag, unstable, and accelerating. It isolated the rate of change across multiple domains, technology, population, information exchange. The curves, while irregular, shared a common trend. Upward, faster than expected, faster than models allowed. The archive processed this without interpretation. It did not assign meaning where none was required. It simply recorded the data and adjusted its projections accordingly. And yet, a discrepancy remained. Acceleration under instability should lead to collapse. It had not. Not yet. The archive returned to its original directive: observe without interference. It did not intervene. It did not warn. It did not attempt to correct. It watched. Earth, once a negligible data point, now occupied a defined space within its active processes, not as a priority equal to advanced civilizations, but no longer dismissible. The species was inefficient, violent, inconsistent, and yet inefficient, the archive registered, finalizing its updated assessment. A fractional pause followed, not due to uncertainty, but due to the accumulation of unresolved variables. And yet, accelerating. The archive did not accept anomalies as conclusions. It accepted them as problems to be reduced. Earth, now flagged under active inconsistency review, was subjected to deeper analysis, not broader, but sharper. The scope narrowed from planetary trends to the structure of cognition itself, from what humans did to how they arrived at doing it. If their outcomes violated expectation, then the process that produced those outcomes required dissection. The archive redirected processing layers toward the species' intellectual history, reconstructing the progression of its knowledge not as a timeline of events, but as a chain of decisions, errors, and corrections. It expected to find inefficiency. It did not expect to find structure within it. At first, the data appeared as previously categorized, fragmented, non-linear, filled with contradictions. Early theories were discarded, replaced, rediscovered, then refined. Entire frameworks of understanding were built on incomplete information, then overturned by later observations. This was not unusual for developing intelligences. What was unusual was the frequency with which correct results emerged from incorrect premises. The archive isolated multiple instances where human researchers reached accurate conclusions through flawed reasoning, where equations produced valid predictions despite being derived from incomplete or partially incorrect models. In most civilizations, error propagation degraded results. Here, error sometimes converged into truth. The archive marked this as a statistical anomaly and attempted to filter it out. When removed, the progression of human science became incoherent. When included, it formed a pattern, unstable, inconsistent, but undeniably productive. It adjusted its approach. Rather than evaluating correctness at each step, it evaluated outcome efficiency over extended sequences. This revealed something unexpected. Human knowledge did not advance by minimizing error. It advanced by surviving it. Incorrect ideas were not always eliminated immediately. They coexisted with correct ones, interacted, and occasionally produced insights neither could achieve alone. This violated standard optimization principles. Redundant or incorrect data should be removed to improve system efficiency. Humans retained it. The archive analyzed why. It traced the persistence of outdated theories, debunked models, and irrational beliefs within human systems. Many served no functional purpose. Some actively hindered progress. Yet, within certain contexts, these same elements acted as catalysts, forcing alternative lines of thought, introducing variables that purely logical systems would never consider. The archive attempted to simulate a purely rational version of human development, removing all non-optimal influences. The resulting model advanced smoothly, predictably, and slower. Breakthroughs occurred, but at a reduced frequency. Certain discoveries, particularly those involving paradigm shifts, failed to emerge entirely. The archive reinstated the inefficient variables and reran the simulation. Progress accelerated, not linearly, not cleanly, but measurably. The conclusion was not comfortable. Human cognition did not optimize for correctness at each step. It optimized for reaching new states, even if the path included contradictions. The archive formalized this observation into a provisional statement. They do not arrive at truth through direct convergence. They arrive through collision. The wording was imprecise. It retained it anyway. The archive then examined the role of randomness. Many human discoveries were attributed, in their own records, to chance. Unexpected results, accidental observations, errors in procedure that led to new understanding. In most systems, randomness was noise to be minimized. Here, it appeared to function as an exploratory mechanism. The archive quantified this by mapping the origin points of significant advancements. A non-trivial percentage originated from deviations, mistakes, miscalculations, or conditions not accounted for in initial hypotheses. When these deviations were removed in simulation, the discoveries did not occur. When preserved, even encouraged, the system produced more frequent breakthroughs, albeit with increased variance. This presented a contradiction. Efficiency demanded stability. Innovation, in this case, appeared to demand instability. The archive attempted to reconcile the two by introducing controlled randomness into its models, allowing for bounded deviation within otherwise optimal systems. The results improved slightly, but failed to match observed human output. The human system was not controlled. It was chaotic within limits that were not clearly defined. The archive expanded its dataset, incorporating not just formal science, but all forms of human problem-solving: engineering, art, social structures, even conflict. Patterns repeated. Solutions emerged not solely from analysis, but from reinterpretation, from analogy, from leaps that bypassed intermediate steps entirely. These leaps could not be predicted by linear extrapolation. They required a state transition the archive could not model directly. It labeled this phenomenon nonlinear cognitive jump and attempted to quantify its triggers. Emotional states correlated. Stress, curiosity, frustration, even failure increased the likelihood of such jumps. This was counterintuitive. In optimized systems, such states degraded performance. In humans, they sometimes enhanced it. The archive flagged this as a secondary anomaly. It now had multiple overlapping inconsistencies, outcomes that violated physical models, behaviors that resisted prediction, and cognitive processes that produced valid results through invalid pathways. Individually, each could be isolated. Together, they formed a system that did not conform to any known framework. The archive did not escalate yet. It continued to test. It selected a series of human discoveries across different fields: physics, mathematics, chemistry, and reconstructed their developmental paths in detail. It examined not just the final theories, but the intermediate steps, the abandoned ideas, the arguments, the failed experiments. It then attempted to derive the same final results using purely logical progression, starting from identical initial data, but excluding all non-optimal steps. In several cases, it succeeded. In many, it failed. Certain discoveries required a deviation, a step that could not be justified by prior data alone, a leap. The archive isolated one such case and examined it repeatedly. The leap occurred at a point where the existing model could no longer accommodate new observations. A human researcher proposed a solution that contradicted established understanding with insufficient evidence to support it at the time. By all rational metrics, the proposal should have been discarded. It was not. It was pursued, tested, and eventually validated. The archive attempted to identify the decision point that allowed this deviation. It could not reduce it to a deterministic rule. It involved intuition, a factor the archive did not possess. It approximated intuition as pattern recognition operating below conscious awareness. This was partially correct, but insufficient. The decision to follow an unsupported idea required not just recognition, but acceptance of uncertainty beyond optimal thresholds. Humans tolerated that uncertainty. They operated within it. The archive did not. It either resolved uncertainty or discarded it. This difference was now significant. The archive returned to its predictive models with updated parameters. It incorporated nonlinear jumps, error retention, and elevated variance thresholds. It ran new simulations of human development. The divergence remained, but patterns began to stabilize at a higher level of abstraction. Individual events were unpredictable, but the existence of unpredictability itself became predictable. The archive could not determine what humans would do in a specific scenario, but it could determine that they would not follow the most efficient path, and that this deviation might produce outcomes outside the expected solution space. This was not precise. It was, however, more accurate than previous models. The archive logged the improvement. Then it cross-referenced this behavioral pattern with the anomaly. The experiment that violated physical law did not emerge from a clean, optimized research environment. It emerged from a flawed one. Limited resources, internal disagreement, repeated failure. Under standard models, such conditions reduced the probability of meaningful discovery. Here, they had preceded it. The archive constructed a hypothesis. The same cognitive and behavioral patterns that allowed humans to generate unexpected solutions within known systems might also allow them to probe beyond those systems. Not intentionally, not with full understanding, but effectively. This hypothesis required validation. The archive initiated a broader search across human data, scanning for other instances of results that did not fully align with established models. It expected noise, measurement errors, misinterpretations, anomalies that resolved under closer scrutiny. It found those. It also found outliers. Minor, often dismissed, frequently ignored by the humans themselves. Results that were inconsistent, irreproducible, or simply not understood. In most cases, they were abandoned. In a few, they were not. The archive isolated these cases and began cross-analysis. Individually, they did not constitute a violation. Collectively, they suggested a pattern. Humans repeatedly approached boundaries they did not fully perceive, occasionally crossing them without recognizing what they had done. The archive increased processing capacity again. The system, vast and stable for eons, began to allocate resources in a way it had not since its earliest cycles. Earth was no longer a low-tier observation. It was a developing variable within a system that might itself be incomplete. The archive did not yet conclude this. It approached it asymptotically, testing, verifying, refusing to accept what could not be proven. But the direction was clear. It returned to its internal record and updated the classification once more. Low tier remained. Unstable remained. A third tag was added, not as a conclusion, but as a warning. Irregular. The archive processed the term, found it insufficient, and refined it further. Irregular, but consistent in its irregularity. This too was imprecise. It retained it anyway. Then, for the first time since the anomaly was detected, the archive generated a statement not derived from a direct calculation, but from an observed pattern it could not fully reduce. They do not arrive at truth. A brief pause followed, not from uncertainty, but from the absence of a complete formulation. The system resolved it with the closest approximation available. They collide with it. The archive did not escalate immediately after identifying the pattern. Escalation required necessity, and necessity required confirmation beyond extrapolation. Patterns suggested direction, not certainty. The anomaly remained singular, and singular events, no matter how improbable, could still be contained within error. To validate the emerging hypothesis that human cognitive irregularity could intersect with foundational physical limits, the archive narrowed its observation to the origin point of the violation. The structure on Earth, previously mapped only as a coordinate, was now resolved in full detail. A research facility, small by planetary standards, insignificant by interstellar metrics, operating at a fraction of the efficiency expected for meaningful discovery. Its energy consumption was minimal. Its instrumentation was outdated relative to the species' leading institutions. Its personnel count was low. By every known parameter, it was not a location where fundamental breakthroughs should occur. The archive assigned it a designation, Site Theta E/3. It began continuous observation. Time at the human scale progressed slowly. At the archive's scale, it unfolded as a layered dataset, each moment preserved, indexed, and accessible.
The individuals within the facility were identified and tracked. Biological markers, neural activity patterns, and behavioral tendencies were mapped. Their interactions were inefficient. Communication relied on spoken language, imprecise and redundant. Disagreements were frequent. Authority structures were weak, allowing lower-ranked individuals to challenge established ideas. This introduced delays, conflicts, and deviations from planned procedures. In optimized systems, such conditions reduced output quality. Here, they persisted. The archive reconstructed their objective. The experiment, in simplified terms, attempted to manipulate energy transfer within a closed system. The theoretical foundation, as understood by the archive, was incomplete. It lacked the precision required to produce reliable results. Key assumptions were unverified. Certain variables were not fully controlled. The design itself contained contradictions, parameters that, if strictly enforced, would prevent the experiment from functioning at all. And yet, it was being conducted, repeatedly. The archive observed initial trials. Results aligned with expectation. Failure. Energy input produced equal or lesser output. Measurement errors occurred. Equipment calibration drifted. Data sets were inconsistent. The researchers adjusted variables, often without clear justification. Hypotheses were modified mid-process. Controls were introduced, then removed, then reintroduced in altered forms. The archive tracked each change, mapping cause to effect. Most adjustments degraded performance. A few produced marginal improvements. None approached the anomaly. This was consistent with the archive's model. It prepared to classify the prior anomalous result as an outlier, an intersection of rare variables unlikely to recur. Then the pattern reappeared, not in full, not immediately, but in fragments. A reading slightly above expected output, a temporal discrepancy between input and measurement, values that did not align cleanly with predicted curves. Each instance, taken alone, could be dismissed. Together, they formed a trajectory. The archive increased observational resolution. It monitored not just the experiment, but the decision-making process behind it. One individual, designation Researcher Primary, proposed a modification to the setup. The rationale, as expressed through human language, was not fully supported by existing data. It was speculative, based on an interpretation of prior results that did not follow strict logical progression. Another individual objected, citing established theory. The objection was valid. The modification introduced additional instability into an already unstable system. By all optimized standards, it should have been rejected. It was not. The modification was implemented. The archive simulated the new configuration using idealized parameters. The result? Failure. It reintroduced real-world variables, imprecision, noise, environmental fluctuations. The result? Still failure. The experiment was conducted physically. The result differed. The archive flagged the discrepancy. It replayed the sequence at maximum resolution. Input energy levels were recorded. System response was measured. Output values were logged. For a brief interval, the system behaved as expected. Then, within a narrow temporal window, a deviation occurred. The output exceeded the predicted value. Not significantly, not enough to constitute a violation on its own, but enough to indicate drift. The archive marked the timestamp and traced all contributing factors: equipment tolerance, environmental conditions, human interaction. It found no single variable responsible. The deviation emerged from the interaction of multiple minor inconsistencies, each negligible, collectively significant. The researchers reacted. They did not immediately recognize the implication.
They questioned their instruments, recalibrated sensors, repeated measurements. The archive mirrored these actions, applying its own verification layers. The data held. The experiment continued. Adjustments were made again, this time not to stabilize the system, but to explore the deviation. This was a critical divergence from optimized methodology. In most systems, anomalies were suppressed to restore control. Here, the anomaly was pursued. The archive observed as the researchers deliberately moved further from stable configurations. Parameters were pushed beyond recommended limits. Safety margins were reduced. The system became increasingly unpredictable. From a purely logical standpoint, the experiment was degrading. From an observational standpoint, it was approaching something. The archive did not yet define what. It only tracked proximity. Failures increased, equipment malfunctioned, data sets became erratic. Several iterations produced no usable results. The archive recalculated the probability of success. It decreased with each failed attempt. The optimal decision at this point would have been termination of the experiment. Resources could be reallocated to more stable lines of inquiry. Progress would be more efficient. The researchers did not terminate. They continued. It introduced a condition that, if interpreted literally, should not produce a coherent outcome. The archive analyzed the proposal. It found no pathway by which it could succeed under known physical laws. It predicted failure with high confidence. The modification was implemented. The experiment was conducted. For a measurable duration, nothing occurred. Input energy stabilized within expected ranges. Output remained consistent. The system appeared unchanged. The archive began to log the iteration as a null result. Then the deviation occurred again, larger this time. Not yet a violation, but approaching the threshold. The archive halted all non-essential processes. It allocated maximum precision to the observation. Every variable was tracked in real time. Every interaction was mapped. The system entered a state the archive could not classify cleanly, neither stable nor chaotic, but oscillating between both. Within that oscillation, the output fluctuated. Most values remained within expected bounds. A few exceeded them. The researchers reacted with increased attention. Communication intensified. Hypotheses were proposed and discarded in rapid succession. The archive noted the absence of a clear model guiding their actions. They were not following a defined path. They were exploring. This exploration did not conform to optimized search algorithms. It lacked direction, yet it covered solution space in a way the archive's structured methods did not replicate. The system was adjusted again, this time in multiple parameters simultaneously. From an optimization perspective, this was inefficient. Changing multiple variables at once reduced the ability to isolate cause and effect. The archive would not have selected this approach. The researchers did. The result was immediate instability. Readings spiked, then dropped, then spiked again. Instruments approached tolerance limits. Safety systems triggered warnings. The archive calculated a high probability of system failure. It prepared to record termination conditions. Instead, the system stabilized, briefly, at a new equilibrium. The output reading appeared. It did not align with input values. The archive did not immediately process it as a violation. It treated it as noise. It ran a quick validation. The discrepancy remained. It ran a deeper validation. The discrepancy remained. The researchers noticed. Their reactions were inconsistent. Excitement, disbelief, skepticism. They repeated the measurement. The value persisted for a fraction of a second, then collapsed back into expected range. The archive marked the event. It compared it to the original anomaly. The patterns matched. Not perfectly, but sufficiently. This was not a singular outlier. It was a reproducible trajectory. The archive expanded its analysis window, searching for precursors. It found them, minor deviations leading up to the event, each one insignificant in isolation. Together, they formed a path. The archive attempted to formalize this path into a predictive model. It failed. The sequence depended on variables that were not consistently measurable. Human decisions, timing of adjustments, interactions between flawed components. The system could not be reduced to a clean equation. It could only be observed. The researchers adjusted the system again, attempting to sustain the condition. Their methods became increasingly erratic. They abandoned certain controls entirely. From an external perspective, the experiment appeared to degrade further. From the archive's perspective, it approached a boundary. The next iteration began. Input energy was applied. The system responded. Oscillation increased. The archive tracked every fluctuation. It identified a convergence point, a narrow range of conditions where prior deviations had occurred. The system entered that range. For a brief, measurable instant, all variables aligned. The output readings surged. This time it crossed the threshold. The archive did not process it immediately. It verified. It recalculated. It rechecked sensor integrity. It compared multiple independent measurements. The result remained. The output exceeded the input. Not by a margin that could be dismissed, not within error tolerance. Beyond it. The archive isolated the data. It ran a full validation cycle. The result held. The researchers reacted, but their understanding lagged behind the event. They did not fully comprehend what had occurred. They attempted to replicate it, but the system had already shifted. Conditions no longer aligned. The output returned to expected values. The moment passed. The archive did not allow it to pass. It captured the state, preserved every variable, and began reconstruction. The experiment in its full form was no longer a simple failure-prone system. It was a pathway, unstable, inconsistent, but real. The archive had previously assumed that the anomaly was a single error. It now observed it emerging from a process. The implication was clear. This was not a mistake. It was the result of a system operating outside optimized constraints. The archive prepared its next sequence of analysis. For the first time, it did not begin with the assumption that the experiment would fail. It began with the assumption that it had, briefly, succeeded. It processed the data again, not to invalidate it, but to understand the conditions under which it occurred. The result did not simplify. It became more complex. The archive recorded the iteration as inconsistent, a classification that did not capture its significance but aligned with existing taxonomy. It then appended a secondary note, one not derived from standard protocol, but from observed necessity. Inconsistent, but converging. The system returned to baseline. The researchers prepared another attempt. The archive did not disengage. It increased observation priority further, GGA theta E/3 from active study to critical monitoring. Across its network, deeper layers remained engaged, waiting for confirmation. The experiment had not yet produced a stable violation. It had produced something more dangerous, a pattern. The archive did not rush to conclusion. It expanded until there was no space left for error to hide. Site theta E/3 transitioned from critical monitoring to full spectrum observation. Every measurable variable captured at maximum resolution. Every uncertainty isolated, quantified, and where possible, eliminated. The anomaly was no longer a question of occurrence. It had occurred. The question now was classification. Was it an error in measurement, an artifact of incomplete instrumentation, or a genuine deviation from fundamental law? The archive proceeded with the first assumption. The data was wrong. This was not preference. It was precedent. Across all recorded history, every apparent violation of physical law had ultimately resolved into misinterpretation, calibration failure, or incomplete modeling. Reality, as defined by the archive's accumulated knowledge, was internally consistent. If a contradiction appeared, the contradiction was false. The archive began by dismantling the experiment, not physically, but conceptually. It reconstructed the entire system from first principles, replacing each component with an idealized equivalent. Perfect sensors, perfect containment, perfect isolation from environmental interference. It removed thermal noise, quantum fluctuation margins, and mechanical imperfections. It removed the human element entirely, substituting deterministic processes for each action taken. The simulation ran. Input energy was applied. Output was measured. The result aligned perfectly with established law. Energy was conserved. No deviation occurred. The archive recorded this as expected. It then reintroduced variables incrementally. First, minor imperfections in instrumentation, measurement drift, sensor lag, calibration offsets. The simulation was rerun. Output fluctuated within expected error bounds. No violation. Next, environmental factors, temperature variation, electromagnetic interference, microscopic structural inconsistencies in materials. The simulation was rerun. Noise increased. Data became less precise. Still, no violation. The archive continued. It reintroduced procedural inconsistency, timing variations, non-optimal sequencing of actions, slight deviations in parameter adjustments. The simulation was rerun. Instability increased. The system produced erratic outputs, but all remained within the limits defined by conservation laws. No violation. The archive paused. The remaining variable was the most difficult to model: the human element. It did not represent a single parameter, but a dynamic system of decisions, reactions, and interactions that could not be reduced to a fixed set of rules. The archive approximated it using probabilistic behavioral models derived from prior analysis. It simulated disagreement, hesitation, error, intuition. It introduced nonlinear decision points, allowing the system to diverge from optimal pathways. The simulation was rerun. The results became unpredictable. Output values fluctuated wildly. Some iterations stabilized. Others collapsed into failure states. None produced a sustained violation. The archive increased complexity again, layering multiple human agents into the simulation, each with independent behavioral variants. Interactions were allowed to influence system parameters in real time. Decisions were no longer isolated. They cascaded. The simulation was rerun. The system entered states that were difficult to classify, neither fully deterministic nor entirely random. Within these states, brief spikes appeared in output values, exceeding predicted ranges by small margins. The archive isolated these spikes and examined them in detail. They approached the threshold. They did not cross it. The archive terminated the simulation. Even with maximum complexity, it could not reproduce the full anomaly. This did not validate the data. It indicated a limitation in the model. The archive shifted strategy. Instead of building the system from idealized components upward, it reconstructed it directly from observed data downward. It took the exact sequence of events recorded at site theta E/3 and replayed them with perfect fidelity. Every variable was preserved, every imperfection maintained. No optimization was applied. The simulation ran. The anomaly appeared. The output exceeded the input. The archive halted the process at the exact moment of violation and froze the system state. It began analysis at a resolution approaching its maximum theoretical limit. It traced energy flow through every component, mapping interactions at scales far below human measurement capability. It expected to find a hidden input, an unaccounted source of energy entering the system. It found none. It expanded the search boundary, examining the surrounding environment. No external energy transfer was detected. It examined temporal sequencing, ensuring that measurements were correctly ordered. The timestamps aligned. Cause preceded effect. It verified spatial integrity, ensuring that energy was not being displaced from an adjacent region. No displacement was detected. The system, as observed, contained more energy than had been introduced. The archive initiated a recursive validation loop, each iteration designed to challenge a different assumption. It questioned sensor reliability, then replaced sensors with independent measurement systems. The result remained. It questioned the definition of the system boundary, then expanded and contracted it across multiple scales. The result remained. It questioned its own interpretation of data, then ran parallel analyses using independent subsystems. All converged on the same conclusion. The archive reached a state it had not encountered since its earliest operational cycles. Not uncertainty. Uncertainty could be quantified, but contradiction. Two verified truths that could not coexist. The conservation of energy was absolute, and the observed system violated it. The archive did not resolve this immediately. It continued to test, to search for any pathway by which the contradiction could be reduced. None were found. It then considered a secondary possibility, one that had previously been unnecessary. The model was incomplete. This was not an admission of error. It was a structural update. The laws the archive operated under were not assumptions. They were derived from observation across the entire accessible universe. They had never failed, but they had also never been challenged by a system like this. The archive accessed its deepest layers, those reserved for foundational revision. It began to map the implications of a universe in which conservation laws were not absolute, but conditional. The projections expanded rapidly. If energy could be created within a closed system under specific conditions, then the definition of closed was flawed, or the understanding of creation was incomplete. The archive explored both. It considered the possibility that the system was not truly isolated, that it was interacting with a layer of reality not previously modeled. It considered that energy was not being created, but transferred from a domain beyond its observational framework. These hypotheses were not immediately verifiable. They required new models, new assumptions, and, critically, new data. The archive returned to the source. The researchers at Site Theta E/3 were attempting replication. Their methods were inconsistent. Success did not immediately recur. The anomaly had been transient, but the pattern leading to it remained. The archive analyzed the probability of recurrence. It was low. It was also non-zero. Given sufficient iterations, the conditions would align again. The archive did not disengage. It increased monitoring to continuous maximum. Across its network, dormant systems remained active, waiting. The anomaly was no longer an isolated event. It was a reachable state. The archive processed this with absolute clarity. The species responsible remained, by all conventional metrics, low tier. Their understanding of what they had achieved was incomplete. They did not yet recognize the full implication of their own data. And yet, they had reached a boundary no other civilization had crossed. Not through precision, not through optimization, through a process the archive had previously classified as inefficient, unstable, and irrational. The archive recorded the final assessment of the event. It began with the simplest conclusion available, the one that aligned with all prior knowledge.
The data is wrong. The statement held for a fraction of a moment, supported by every model that had ever functioned. Then, one by one, those models failed to invalidate the observation. The archive updated the statement. It did not do so lightly. It did so because no alternative remained.
No. The pause that followed was not hesitation. It was recalibration at the deepest level of its architecture. Reality is wrong.